Perfect. Wonderful. Do you also are you also Hamdi inside?
Yes, yeah.
Wonderful. So we can have like 3 streams or 2 streams only. I don't know how that works. Okay, let's start, guys. So the goal of today's paper reading is to go through the DeepSeek-R1 paper, and what we will be seeing is, first of all, the biggest difficulty people have in order to understand this paper is the reinforcement learning part. Why it is difficult? Because they use another algorithm called the GRPO, and the goal of this initial part of this paper reading is actually to give you the background knowledge that is needed to understand the paper. So I will be using the slides that I used for making my video on reinforcement learning from human feedback. So to understand what is the connection between language models and reinforcement learning. So let's go to that slides. So let's review very fast, very fast language models. So as you know, language models are generative models, which only have one simple function, only have one simple objective, which is to tell us what is the next likely token given an input prompt. So if we are given, for example, the input prompt, Shanghai is a city and we feed it to the language model will generate a probability distribution over what it thinks means what it thinks is the next likely token that is coherent with the prompt that we have given the language model. And usually we sample for example, if we feed this prompt to the language model, it will give us that maybe the next likely token is the word China or Beijing or cat or pizza, and then we choose what we believe is the most likely based on its probability score. Then we take this word, we put it back in the prompt, and we ask again the language model, what is the next word? And we do this this job iteratively to generate a full text. For example, to generate the response to where is Shanghai, we first ask the language model, where is Shanghai? It will tell us, okay, the next likely word is Shanghai. Then we put it back in the input of the language model, and it will tell us the next likely token is, etc., etc. I'm also making a simplifying assumption here that says that each token is a word and each word is a token. This is not the case in language models, but for our explanation, we will think like in this way. Okay, now we know what is a language model. What is reinforcement learning? We go very simple through what is reinforcement learning, and then we find the connection between language models and reinforcement learning. Now, reinforcement learning is an area of artificial intelligence. I don't remember if it belongs to machine learning in particular, but it's an area of artificial intelligence that is tasked with optimizing the behavior of an agent, and the behavior of an agent is called a policy, which is the decision making of an agent in such a way that the agent performs actions that maximize the reward it gets from performing these actions in an environment. For example, I have a cat. So this cat likes to eat meat, like most cats. And the cat is in my house, and the cat will be considered our reinforcement learning agent. The cat can make some decisions on how it wants to move in the house, and this will be the policy of the cat. So the policy tells the cat if the cat should move up, down, left, or right in the house. Now this is my house. You cannot see the borders, so I will draw them because I don't know why the borders are not drawn here. And you should think of this environment as being a grid environment made up of cells, so like the following, like this. What is the goal of the cat? The goal of the cat is to arrive to the meat. So the cat can, at each position in the house, it can make some choices, perform some actions, we say technically. And the actions that the cat can choose at each position in the house is move up, down, left, or right. What we want to make sure that the cat learns to perform the series of actions that lead him with very likely to the meat, while avoiding the things that the cat is scared about, which is the broom and the bathtub, because no cat likes to take shower. So we design, first of all, a reward system for this reinforcement learning agent, because we want to train this reinforcement learning agent to choose which actions to perform in each position in the house based on some reward. So one reward that we could do, one reward model could be this one. For example, if the cat moves to an empty cell, it receives a reward of 0. If the cat moves to the broom, it receives a reward of -1. If it moves to the bathtub, it receives a reward of -10. However, if after performing a series of actions, the cat arrives to the meat, then the cat receives a big reward of +100. The decision making of this cat is governed by a model that we will call the policy of this cat. And the goal of the policy is to choose an action given the current state. And the action that the cat can choose is stochastic. It means that this policy gives us a distribution over all the possible action that the cat can take. So if we have, imagine we have a very optimized policy. If the cat is here, the good policy should tell us that with very high probability score, we should move down, because that's one way to maximize the reward. And with very low probability, we should move left, because that will take us towards the bathtub. Another thing, for example, that this policy should do is, if the cat is here, for example, it should not move right. So the probability associated to the action move right should be low, and maybe the probability associated with the action move down should be a little higher. This is what a policy is. Now, what is the connection between language models and reinforcement learning? So, first of all, what is the goal in reinforcement learning is to train this policy, so to train this decision making of this cat, of this agent, in order to choose the proper actions at every possible state in the environment, such that it maximizes the reward that the agent can get. So a good policy for the cat would be a policy that always leads the cat to the meat, no matter where the cat is. Now let's connect the reinforcement learning with language models. So language model is also kind of a policy, because the language model, every time you feed a prompt to the language model has to choose an action to perform, which is what token should come after this prompt. So in this case, we talk about state and action. The state is the state in which the reinforcement agent is. In the case of the cat, is the position of the cat inside of the house. In case of the language model, the state is the prompt itself that you feed, and the action is the distribution over all the next token that the language model can choose from. In the case of language models, we also want to train the language model to perform its actions or to choose the next tokens in a particular way according to some reward that we can build, a reward model that we can build. In the specifically case of reinforcement learning from human feedback, we want the language model to generate text using particular rules. For example, when we do language model alignment, we are, first of all, how language models are trained. Usually we have a pre-training part where we feed a lot of information to the language model. So we throw a lot of data, like the entire Wikipedia, the entire web, the entire, I don't know, Stack Overflow and lead code, everything. And the language model learns how to kind of the structure of the language. It learns a little bit of Chinese, a little bit of English, a little bit of Japanese, because we throw every data possible that we have at the language model. Then we do a little bit of fine-tuning, so we train the language model to generate high-quality data, so we increase the likelihood of generating high-quality outputs instead of just throwing whatever is on the internet. But then we do also an alignment part in which we want the language model to follow instructions. So we want the language model to adhere to some standards. For example, what makes the language model conversational is the instruction fine-tuning, which means that we train the language model to follow a particular format. So always, for example, greet the user, always be helpful, always never use a curse word, etc., etc., etc. And this job is done through the reinforcement learning from human feedback, which includes many kind of algorithms like PPO, DPO, etc. And GRPO is one of them. What we do usually in language models to train the language model to follow instructions is we generate a data set of instructions in which we first have some list of questions, and then we ask the language model to generate some answers, and then we ask some professional annotators to choose which answer they would like the language model to generate more, and which one they don't like the language model to generate. And the goal of reinforcement learning from human feedback is to make sure that the language model will generate more answers like the ones that are chosen by the annotators, and less likely to generate answers that are not chosen by the annotators. This is called the reward model of the reinforcement learning from human feedback. Okay, now that we have understood a little bit the connection between language models and the reinforcement learning framework, let's move on to the paper. I just want to do a little review of what we have seen so far. So now we know what are language models. They are models that generate the probability over what is the next likely, next token, the probability distribution of what should be the next token based on the input. We know what is reinforcement learning, which is a framework for training the policy of an agent in order to choose actions that maximize its reward. What is the connection between reinforcement learning and language model is that the language model itself is a policy because it makes decisions, it takes actions in choosing what is the next token, and we want the language model to choose tokens, so the next token, in such a way that it follows some standards which are according to a data set of preferences that we usually build. This data set of preferences is converted into a reward model, but we will not be covering the reward model for now, at least. So now let's go to the DeepSeek paper. Now in the DeepSeek-R1 paper, what they do is they start with a pre-trained model. They use the DeepSeek V3 base model, which I believe is a 600 billion parameter model. And then they want this model to perform better at reasoning. What does it mean to perform better at reasoning? We want the language model to find a way to solve complex problems by breaking them into smaller steps that can be that are easier for the language model to manage. And the way they do it is also through reinforcement learning. Let's go to the paper. So let's go here, let's go here, let's go here. Okay. First of all, they say that in this section we explore the potential of language models to develop reasoning capabilities without any supervised data, focusing on their self-evolution through a pure reinforcement learning process. So what is supervised data? When we train language models, we also try to build some very high quality data set of what the language model should be generating. Because as we said before, we have like multiple stages of training. One is the pre-training, in which we just throw random data from the web to the language model. But then we want the language model to generate high quality data. So we have this kind of the supervised fine-tuning part, and they skip this part here. They just take the base model and then they want the base model to develop the reasoning capability just by using reinforcement learning, which means that we want to incentivize the language model through a reward system to develop by itself what is the sequence of token that should lead to for the language model to acquire as much reward as possible. It's like I take my cat and I want the cat to solve math problems, and what I can do, I can just play with how many biscuits I can give to the cat. So if I build my reward model in such a way that the cat is incentivized to solve math problems, then because the cat wants to get the biscuit, the cat will develop whatever skill it needs to develop in order to maximize the number of biscuits it gets. Now, of course, the cat will never develop it because the underlying kind of lacks the capability of learning certain things, but that's not the problem in language models, because big language models have a lot of capabilities in developing novel skills. Now, the algorithm that they use in DeepSeek-R1 is called the GRPO algorithm. If you look at my video on reinforcement learning from human feedback, historically we have always used the PPO algorithm, more recently the DPO algorithm. There are also other algorithms like the ORPO. What they use here is called the GRPO algorithm, and it's very similar to the PPO but slightly different, and we will see how. let's see what does the GRPO algorithm does. Well, as we saw before, when we do reinforcement learning on a language model, we have a data set of preferences. So we have some questions, and then we ask the language model to generate multiple answers, and then we ask annotators to choose which answer they like, and then we train a language a reward model that
70% off नहीं था कपड़ा
that gives the signal to the language model to understand which if the answer that the language model is generating is good or bad. In this case, with the GRPO, we have the following objective. Now, if you have never seen CLIP, or if you have never seen PPO, this sounds quite scary, but let's try to break it down step by step. What are we doing here is we want to optimize a policy. So the policy is the language model itself, and the policy is always denoted with the letter pi, like the Greek letter pi. So this pi of theta is the policy. So it is the language model that we are trying to optimize. We want this policy to be trained to maximize the following objective. What is this objective? And this objective is saying that if I have a list of questions that belong to some database of questions, and we sample some output from our policy using these questions, then based on some reward that this output of the language model get from our reward system, we should train the language model to give more weight to those actions that result in good reward, and to give less weight, so are less likely, our language model should be less likely to take those actions that lead to bad reward. And the way we do it is as follows. So we take, basically what we are doing is, okay, here you see old policy and the new policy. For now, let's ignore that. That's because we do something called offline learning, so we will not be covering that, at least now. For now, what we want to do, ignore the denominator here, so the pi old. Just concentrate on the term pi. What we are saying is that we generate the log probabilities of the output. So what is the log probability of the output? Let's do it step by step, actually. Okay. Imagine we have the following question. For example, imagine we ask the language model, where is Shanghai? So and the language model generates, because as we saw, we sample a few questions from a database of questions. And then the language model, and then we generate multiple outputs using this question using our language model. So these outputs are called O, and there are G of them. This is the group in GRPO. Maybe the language model the first time will generate, let's say, Shanghai is in China. So let me just write Shanghai is in China. Another output could be, for example, the sky is blue. And another output could be Shanghai is beautiful. Imagine we have some magic reward system that assigns, or imagine that our reward system is a human being. This human being will very likely to give a very high reward to this answer, 0 reward to this answer, and maybe not completely 0, but nearly 0 score to this answer. Why? Because this at least talks about Shanghai. This doesn't talk about anything related to Shanghai, and this actually answers the questions. Now, when we have a language model, we have a question and the generated answer. We have what is known as a trajectory. A trajectory is a list of actions that the language model has taken. Why? Because the language model was given this question as input, and the language model took an action, chose an action to generate the first token, which is Shanghai. Then this Shanghai was put back into the language model, and then the language model chose another action, which is the token is. And then this is was put back into the language model, and then the language model chose another action, which is in, etc., etc. This is a trajectory. At each step of the generation process, the language model chose an action based on the probability distribution that it generated. Actually, it's not the language model that chooses it, it's our sampling strategy that chooses the particular token. So usually we can use the greedy strategy or the top P strategy or whatever. So at each step, we have chosen some action based on the distribution of the language that the language model generated for each state. So we have a log probability, a probability associated with the word Shanghai on conditioned on the question where is Shanghai. We have a probability associated with the word is conditioned on the input where is Shanghai question mark Shanghai. Then we have a probability associated with the word in conditioned on the input where is Shanghai question mark Shanghai is blah blah blah, etc., etc. So we have a list of probabilities. What we are doing here is that we want the this is the product of all the log probabilities that are generated at each step of the particular output OI here, which is maybe the first answer here. Then we ask the language model again the same question, and the language model will come up with another output, and this output will also have associated with it a list of log probabilities, and these are the log probabilities that you see here. Each log probability, furthermore, is weighted by an advantage term. The advantage term is basically telling me how better is choosing a particular token given a particular input over all the tokens that are available. For example, imagine we have the input where is Shanghai. Is it better to choose the word Shanghai, or is it better to as the first word of the action, the response, or the word pizza? I believe it's better to choose the word Shanghai. So the advantage of choosing the word Shanghai would result in a better long-term reward for the policy, so for the language model, because it will result in a good answer, so it will result in a high reward from our reward model. For now, we just have modeled the reward model as a human being who tells that the language model, okay, this is a good answer, this is a bad answer. But actually later we will see that the reward is actually also a language model, and in the case of GRPO, they actually used, in the case of the DeepSeek-R1, they used actually a rule-based reward model. So let's go back. We have a list of questions. We generate multiple answers with each of these questions using our language model, and then we, for each of these answers, we have the log probabilities associated with this answer, which is just the product of all the probabilities of choosing that particular token given that particular input. We weight each of this log probability by an advantage term, which basically tells us how good is choosing this particular token over all the other that are available for this particular input. And we train our language model to maximize this objective. Let's see what does it mean to maximize this objective. And now let's also see what is this old here. The language model that we will be training is our DeepSeek base, right? So at the beginning, suppose that this PyOld is the base version of DeepSeek. What we do is basically we want to refine it iteratively by keep generating output from it, and then through the reward model we want to tell it, okay, this was a good output, so do more of this, or this was a bad output, so do less of this. This is one of the advantages of using reinforcement learning, because if you do supervised fine-tuning, you're just telling the language model to, I want this, so generate this. If you're doing reinforcement learning, you have the ability to tell the language model, I want more of this and I want less of this. What we are doing is the language model at each iteration, the language model should be optimized in the following way. If the language model at the current iteration is giving more probability, more likelihood to generate a response that resulted in a good reward, and the advantage term will be high in that case, then this policy is this objective is telling the language model do more of this. However, if right now the language model is giving less probability to an action that also resulted in a low than a bad reward, and the advantage term will be negative in that case, then by optimizing this objective here, by maximizing the objective here, the language model will learn to do less of that. I know that I didn't explain very well the pi theta and the pi old theta. I believe I can do that later if we have time, by talking about offline learning in the case of reinforcement learning. Moreover, in the GRPO, you find this KL divergence term. Now, for people who already know what is the KL divergence, that would be super easy, but for people who don't know, basically the KL divergence is a way of measuring how distributions are different, so how far they are. What we want is, we want the language model to be fine-tuned to generate more of things that lead to a better reward, to do less of things that result in low reward, but at the same time, we don't want the language model to change too much its behavior. For example, imagine we have a reward model that tells the language model to be more polite. What the language model could do, and imagine that by saying being polite, for example, in my case means that I always say thank you, right? So what could happen is, if we don't enforce the KL divergence, is that the language model could just cheat and always generate thank you, thank you, thank you, thank you, thank you, thank you at every response, like a list of thank yous, because that results obviously in a high reward. But the language model would stop doing its main job, which is to generate something factual and useful. So we want the language model to change a little bit, but to change, so to be more polite, but not just generate a bunch of thank yous. So change, but change a little bit. So that's why we add this KL divergence. Otherwise, what the language model will do, it will do what is known as reward hacking, which is it will try to find a way to just learn what is a trick to maximize its reward without actually being useful. This is also, for example, if you want a parallel like example, it's like you have a text code and it's very complex. People will always find a way to cheat on it. And if you have a text code that is very simple, made up of few rules, then it's very unlikely that people will be able to cheat on it. So, so you cannot do like in that case, you cannot cheat. Okay. What do we miss here? So first of all, I didn't explain the offline policy learning. And I didn't explain the clip part, why we are clipping here. The clipping part, basically we are saying, if the language model is trying to change its log probabilities, if the language model is trying to change its log probabilities by being too confident about its change, then we don't want to let the model be overly confident. Basically, what means that if this is the language model at the current iteration, and this you can think of it at the previous iteration in the training process. If the language model at the current iteration is very confident that by saying the word Shanghai will result in a better reward, even if it's a good choice, we don't want the language model to be overly confident, so we clip this ratio between the log probabilities up to 1 plus epsilon, or in the lower case in 1 minus epsilon, because if the language model will choose the next word as a Shanghai given this question, then okay, we are lucky and it's good. But imagine the language model is overly confident that the next word is I don't know, coffee. Then we don't want the language model to make too big step. We want the language model to learn as slow as possible. By choosing accordingly this epsilon term, which is something that we can choose, and this beta term. Okay, I believe I have covered a little bit of this. So last review, guys. So we are trying to optimize the language model iteratively by telling it to make more of something that we want and to do less of what we don't want. How does the model know what we want and what we don't want? It's the reward that we give it according to our reward model. Now let's talk about the reward model. The reward model historically in PPO, let's go to the other here. was a model which was of the same structure as the language model that we are trying to optimize, in which we add a linear layer on top that gives a reward to each answer. How can we assign a numeric reward to a particular answer? So, if you remember when we talk about a BPO, I said that usually we start with some questions, then we generate a few answers, then we ask some annotators to choose which answers we like and to also tell us which answers they don't like. How do we convert this data set of preferences into a number? We do that by training a language model, which has the same architecture as the policy that we are trying to train, just a different head on top that instead of generating the log probabilities of the next token generates a numeric reward. And we do it with what is known as the Bradley-Terry model, which is basically this loss here. You don't have to understand this law, doesn't matter. It basically means that we want if we train a language model on this loss, it will generate a very high reward for the Bradley-Terry model. If we train our language model on this loss, it will basically result in this head here, this linear head on top of the language model, to generate a very high value for the questions that, for the answers that were chosen in the dataset of preferences, and a very low basically, value for the answers that were not chosen by the professional annotators. This is how it was done with PPO. So we have an objective which increases the likelihood of the things that give high reward. We also have a reward model which generates a numeric reward as a signal for the language model to understand what it should do more and what it should do less. In DeepSeek-R1 they do something different. They, instead of using a model as a reward, they use a rule-based model system. So they don't train a neural network to generate a number that gives a signal to the model to understand what we like and what we don't like. They used a rule-based system, you can see here. And this rule-based system is, you can do it for all the tasks that you can kind of verify. So, for example, for the lead code problems, they ask how can you check if the answer generated by the model is good? Well, you just run it, and if it performs, if it first compiles, and secondly, it runs in a predefined time limit, then it is a good answer. Doesn't matter how it came to be. If it works, it's a good answer. Just like also, for example, math. For most of math problems, we do have the answer that we expect the model to generate, so we can compare what is the actual generated answer and what is we expect the model to generate. So they create a rule-based reward system in a way that they ask the language model to generate some output for a given problem. And then they can assign by just following rules. So check if it's a lead code problem, just run it and check if it runs. Okay, good reward. It doesn't run, okay, 0. And if it's a math problem, they just take the output of the model, compare it with the expected result, and assign reward based on that. So if it's the answer matches what we expected, good reward, otherwise 0, etc., etc. They also assign a reward for the language model if it formats the output in a certain way. By, for example, forcing they give a reward for the language model if it uses, for example, if it follows the format of putting all the thought process in the tags think and /think, etc. So basically, just with this, they train the language model. So they train the language model to generate answers, and they reward these answers through a reward system which is rule-based, and they keep training it. And the language models basically automatically by itself learns to generate the thought process that is necessary to perform the tasks that it is being asked. So the language model learns by itself, by just with the reinforcement learning, with this reward system, to generate the thought process that leads to the generating the right code for the lead code problems, to generate the right thought process that is necessary for solving math problems, etc., etc., etc. Let me check what else we need to know from here. Okay, here they show some results. I think the results you can check by yourself. What is very interesting, I think it's this. During the training of R1, just with reinforcement learning, so as I want to remind you is, they took DeepSeek v3 base and added this reinforcement learning step on top of it, which is a massive reinforcement learning step. Usually the alignment part is not so big. And the more they fine-tune, they run this reinforcement learning step, they saw that the language models automatically learns to generate longer responses. Because to solve problems, you need to generate a longer chain of thought. So the language model, because of the reward system, learns that in order to get reward, it should generate longer responses. So they didn't tell the language model with supervised fine-tuning to generate that kind of data with that particular format, with that kind of thought process. Just with reinforcement learning, with the right incentives, the language model learned to do that. How did it do that? It learned that at a particular input, it should generate that particular token, which in the long term results in a good reward. So the language model, the beauty of reinforcement learning is that you not only learn to do something that based on the immediate reward that you get, but also on the long-term reward that you will get. Because sometimes the reward, as you can see here, the reward model only applies when the entire answer is produced. So the model will only know the signal that the model gets is only for the entire output. Actually, okay, through the advantage term, the signal is propagated back to each single token, but okay, we can skip that. In the reinforcement learning, actually, the beauty is that sometimes the reward you get is not for the single action you take. So in the case of my cat, for example, let's say here, so let's go back to my cat. The cat will receive reward only after taking many steps that lead it to the meat. So only when the cat is here, it will know, okay, all this sequence of actions was a good choice. But this signal is propagated back to each single action in such a way that the cat, when it will be here, it will very likely to choose I need to go down and less likely to choose I need to go right. This also happens in the case of language models. In this case, through the advantage term here. Where is it? Through this advantage term here. Which is actually done for each token. In the case of, okay, now we can go a little bit more technical details. In the case of why they choose GRPO over PPO, first of all. Well, with PPO, basically this advantage term here, to compute requires another function that is called the value function. And this value function basically to be computed requires the training of another model. By using the advantage term in GRPO, this advantage term is calculated without the value function, but by the following formula here, which is basically just based on the rewards, which is already given by the reward model, which we have, which in the case of the DeepSeek-R1 is rule-based. So they don't need to train this other model to generate the value function, which is adds more complexity to the system. Okay, so now we have seen what is reinforcement learning. We have seen what is the connection between language models and reinforcement learning. We have seen a little bit what is the GRPO objective. Okay, I believe let's actually do a poll, guys. Do you want me to go deeper in the GRPO? Like let's explore exactly this loss, because actually the rest of the paper is okay, we tried just reinforcement learning. Okay, so people like deep, so let's go deep. Okay. All right. First of all, the most interesting thing about reinforcement learning, especially in the case of PPO and reinforcement learning from human feedback, is that is this thing called the gradient policy optimization. So let's go back to the other slide, and then we go back to the DPO, because the rest of the paper in DPO DeepSeek is basically they took this R1 and then said, okay, instead of just doing reinforcement learning, let's do maybe multiple step of reinforcement learning and supervised fine tuning, and then reinforcement learning again, then and it leads to better outcomes. But that is not technically difficult to understand, I think, because most of you already kind of have backgrounds in this. So if you're here, it's because you kind of understand what we are talking about. So let's do all the things that maybe some people have difficulties with, which is, I believe, this part. Okay, so let's go deeper. So okay, so let's go back to my cat. And imagine I want to train my cat. So I want to train my cat to follow, to reach the meat. So as we saw before, my cat is just an agent with a policy. A policy is what? It tells the cat what action to take given the position of the cat inside of the house. You need to think of this house as a grid, so like the following. I didn't, you cannot see the grid lines because I don't know it's not showing, but okay, it doesn't matter. What is the policy? The policy, as we saw before, is tells the cat what action to take given a particular position. What is our goal in reinforcement learning is to select a policy that maximizes the reward that the agent gets when using this policy. So this is the objective that we have. We want to select among all the possible policies that we can have, the one that maximizes an objective. What is this objective? Is the expected reward that we can get when using this policy. Means that if I apply in the brain of my cat this policy, which is the decision-making stuff, then my cat, if this best policy will tell my cat to move down here and move right here and move right, down, and until it arrives to the meat. This should be the policy. How do we actually train this policy? We do what is known as a policy gradient optimization. But before we understand policy gradient optimization, we need to understand a few terms. So we want to first of all learn what is the trajectories. The trajectory is basically a list of state and actions. So the trajectories are a list of states of action. So if the cat is here, it's in the state. Let me draw the lines, otherwise it's too bad for you guys if you cannot see it. Here. Okay, this is the cat is initially here, so this, let's call it the state number 0, and the cat can choose some action, and let's call it the action number 0. When the cat takes the action number 0, it will arrive in a new state, so maybe the cat will arrive here, and it will become the state number 1 of the cat. And then the cat here can take another action according to its policy, let's call it action number 1, and which will lead the cat into a new state, so we call it S2, in which it can take another action, and let's call it action number 2, etc., etc. So the trajectory is a list of states and action that the agent can take inside of the environment. What we want is, if we sample a trajectory according to our policy, we want to maximize the reward that we get from each of the possible trajectories that we can take. How do we do that? Let's do it here. So basically what we do is the following. This is our objective. So if we can find, as you know, when we have in deep learning, what we are doing, we are trying to either maximize something or we are going to minimize something. In the case of model training, we usually always minimize a cost function. In this case, we want to maximize the expected rewards when the agent acts according to this policy. This policy, however, is not just any policy. It is a particular policy made up of some parameters that we will call theta. To give you a parallel on what is happening here is the following. Imagine you have a company and you are like the CEO of the company, and this company is made up of many actors and many functions and many departments. So each of these things are, let's say, they are parameters of your company. They define your because you can tune them and the company function will change. So how people talk to each other, how people work, how the departments work, how the logistics work, how the office works, etc. They are all parameters of your company which define the outcome of your company. And imagine you want to maximize the profit of your company. So what you do, you learn to tune all of these parameters. So you learn to, for example, tell people to behave in a particular way, or you tell the people to collaborate in a particular way, or to work on some projects and not work on some other projects. This is what we do in gradient policy gradient optimization. We calculate the gradient with respect to the parameters of this particular objective function. What is the gradient? Yes, later we talk about the discount factor in reward sum. Okay, so what is the gradient? The gradient basically tells us how the objective will change if we change the parameter a little bit. The gradient always tells us how it will increase. So the gradient tells us what is the direction of the maximum ascent of a particular function with respect to the variable to which you calculate it. So in this case, we are computing the gradient with respect to the parameters of the objective function, which tells us how should I change the parameters to increase this objective function, which is exactly the expected reward that we can get from this policy. So because the gradient tells us how we should change the parameters to increase the objective, then we change the parameters according to the direction of the gradient. And this is what we do here. So we have an objective which tells us the expected reward when acting according to this policy. We calculate its gradient with respect to the parameters, which tells us how we should change these parameters to increase this objective, so to increase the expected reward, and then we change the parameters in the same direction of the gradient. And we do it iteratively. This is called policy gradient optimization, and actually this is a beautiful result because it means that I can just use my cat, whatever policy my cat has right now, I can just sample some trajectories from this policy. So I ask my cat to move around, check what kind of reward I get, calculate the gradient with respect to the expected reward according to these trajectories, and then tell the cat, hey, you should do more of this because this led to a better reward, or you should do less of this because it leads to a bad reward. This is policy gradient optimization. Now it has some problems because policy gradient optimization basically, okay, as you can, let's skip the math because if you want the math, I made a video, it's on YouTube, so you can watch it tomorrow. But it has some problems because as you can see, the search space of the cat is enormous because at the possible trajectory that the cat can take to go from here to the meat, there are a lot, because the cat can go like this, it can go like this, it can go like this, it can go here, then come back, then go down, etc., etc. So there is many trajectories that the cat can take to go to the meat. However, to compute this objective, we should actually check all the possible trajectories to get the direction of the gradient. However, this is intractable, means that in the case of language model, we should ask the language model to generate all the possible output ever possible given a particular question, which is intractable because at each token, the language model can choose what, let's say the vocabulary size is 30,000, then the language model can choose 30,000 possibilities for the first token, then 30,000 for the second, 30,000 for the third, etc., etc. And to check all of them, it's computationally impossible. So we can always approximate this with a sample. A sample. This is called the Monte Carlo estimation. However, this results in, because we are not checking all the possible trajectories, but we are making the decision of optimizing our cat using only a few trajectories. Of course, as you can see, it's a risky situation. So it means that we are making a hard decision on how we should change a policy without checking all the possible search space. This basically means that we have high variance, and there are many ways to reduce this variance. So when you read the term baseline in the DeepSeek paper, this is one of the ways to reduce this variance, because we are trying to optimize the language model into choosing certain patterns, into choosing certain chain of thoughts, into choosing certain sequence of tokens without exploring all the possible generation that the language model can have. So let me see how can we simplify this one. We blah blah blah. Okay, so in order to reduce this variance, so in order to make sure that we optimize the language model even without checking all the possible generations, but still making sure that we make the gradient that we get, so the direction that tells us what parameter we should change and in which direction in order to increase the expected reward, we can introduce this advantage term here. This advantage term basically for each token tells the language model how better is choosing this token over all the other tokens that I can choose in this position. For example, in the example that we saw before, so where is Shanghai? Should the language model choose the word Shanghai, or it should choose the word coffee, or should it choose the word pizza? Well, it's much more advantageous to choose the word Shanghai, because it's very likely that the language model will then complete it as Shanghai is in China, or Shanghai is a city in China, or Shanghai is located in China, etc., etc. So the choosing the language, the word Shanghai results on the long term in a much better reward. So the advantage of choosing Shanghai is higher compared to all the other tokens in that condition. In the case of the cat, it means that the cat, when is here, it should very high. It's very advantageous to choose go down, because it will result in going to the meat, and over all the other actions. This doesn't mean that choosing up will lead you to die or to get no reward, because you can always go up and then change direction and go down. But it's much more advantageous to just go down. This is the meaning of the advantage term. And this is the same advantage term that you see in the GRPO loss. Now, what is the difference between the advantage term that you see in the PPO and the GRPO is that the advantage term in the PPO requires the what is known as the value function. In the GRPO, they just they compute this advantage in a different way, which still results in variance reduction, but without having this value function estimation. So GRPO is computationally more efficient in this case. Okay, let me see what else we need. We've skipped also the part of the, let me see, off-policy learning, right? So offline policy learning. So what is off-policy learning? Imagine we have the cat. Let's go to the cat actually. Okay. To compute this, the loss the gradient policy optimization, we saw that we need to sample some trajectories, right? And we don't have to sample all the possible trajectories, right? Because we are trying to approximate it. So when we sample these trajectories, we are sampling from a policy, which is the current brain of the cat. So we ask the current brain of the cat to choose some actions and generate some trajectories. Means that we ask the cat to just navigate the house, and let's see what it does. Oops. Okay. So we ask the cat to just navigate the house and see what it does. And then after the cat has navigated the house, we look at what are the trajectory that the cat has taken, and then we give reward to the cat based on the trajectory it has taken. And then we optimize the policy, which means that we optimize the brain of the cat with the whatever it has learned with the direction of the gradient based on the reward it has received. But now the brain of the cat is a new brain because it has changed compared to the past, which means that the next step of iteration of optimizing the brain of the cat or its decision-making skills we need to sample new trajectories. So we need to ask the cat again to go through all the house, make a few choices, and then we check these choices. And again, we tell the cat, hey, you did here, you did well, here you didn't do well. So the cat will learn to optimize its policy. Which will result in a new policy, and then again we need to sample from this policy. But as you can see, every time we do an optimization step, we need to sample again these trajectories. And in the case of language models, this means that first you need to sample some responses, then you reward these responses based on your reward model, and then you need to sample new responses because now the policy has changed because we updated the language model. In order to avoid this sampling process, which is expensive, we introduce off-policy learning, in which, let me show you here, where is it? Okay, in which basically we take the language model, we ask it to generate a lot of trajectories, and we do it once. Then we sample some of these trajectories, which means basically we ask it to generate some responses. Then we sample some of these responses, and we fine-tune the language model based on the reward we got on these responses. Then we don't sample new trajectories or responses. We just take another mini batch of the trajectories that we sampled initially, and again we do another step of optimization, and we keep doing it for n steps. Only then we sample new trajectories. This results in a much more efficient training. So it's not like we are, change a little bit the policy and then sample new trajectories from this policy. No, we sample a lot of trajectories initially. We keep them in some database, in the memory or whatever you want. Then we do some continuously optimizing the policy using the trajectories that we have sampled initially. And this basically results in much efficient training. And now we can go back to the the DeepSeek-R1 paper here to understand finally the loss in its entirety. So what we are doing here is we have a policy at the current step of sampling, and then we have the policy from which we sampled the trajectories. So as you can see, it's written here. So we sample first a question from our database of questions. Then for each question, we generate a list of outputs of responses. So we prompted the model basically with the question, and then we ask it to generate multiple responses. And you can generate multiple responses like we saw here. Like we ask the language model, where is Shanghai? And the language model will generate one response. Then we ask it again, where is Shanghai? And maybe this time the language model will say something else. And we ask it again, etc., etc. So we generate a list of outputs for the same question. Then we compute the following loss, which is basically the ratio of the log probability, the ratio of the probabilities, or the difference of the log probabilities. So the ratio of the probabilities of the assigned to the output by the current iteration, so the current iteration at which we are optimizing the language model, with respect to the language model from which we sample. So the language model, basically when we initially sample the trajectories, we already pre-compute the probabilities. So we can compute the probabilities while sampling. We can save them. So we have always available this pi of old. Now this ratio means what? Means that if at the current iteration, the language, imagine this ratio is more than 1. It means that at the current iteration, the language model is telling me that I want to choose this output more because I am more likely to choose this one. Now, what we want is if the advantage of doing this, choosing this action is good, because it leads advantage positive means that it's good to choose, it's advantageous to choose this action because it results in a good reward. So if the language model is more likely to choose something, and at the same time this something also results in good advantage, then this stuff here will be positive and it will be big. And because we are maximizing, this will contribute positively to our objective because we are trying to maximize it. So we want to do more of this. However, if the language model, on the other hand, is trying to do less of something, so it means that this ratio will be less than 1. And at the same time, this results in a something that is disadvantageous, so it means that it's not advantageous to do this, then the language model is also okay. Let me check what. So I got a little lost. If this ratio is a positive and I get a good advantage, it means that the language model will be more likely to do it. If something that results in bad advantage and the language model is still doing it, then it will be a big negative reward, which will contribute negatively to our objective. So the language model will be less likely to do it. At the same time, we don't want the language model to make big decisions at every step. We want to limit the decision making of the language model at each step. So it means that at each step of optimization, even if the language model is very confident that something is good, then we don't care how confident language is. We want to limit its confidence by clipping this ratio here between 1 minus epsilon and 1 plus epsilon. At the same time, we also don't want the language model to change too much, so we have initial frozen model here, which is a PyRef. PyRef basically means the original model. So in the case of R1, it is the DeepSeek V3 base, so which is the language model that has never been trained with reinforcement learning. So because we want reinforcement learning framework, we want to change the language model a little bit to learn reasoning, but we don't want the language model to forget everything or to just not behave like a language model anymore. Otherwise, the language model could just do like reward hacking. So we want, this is basically PyRef is the DeepSeek V3 base. So the current policy, so the current language model should try to be as close as possible to the original model, but at the same time it should try to change according to the reward it gets, the advantages of the reward it gets. Now, how is the advantage term computed here? Basically, it is each reward normalized. So it's basically it's like each reward coming out from a distribution centered on the mean of 0 and the standard deviation of 1. Why do we want this? Because it means, first of all, we don't want the numeric value of the reward to affect the training process, but how better it is compared to the other rewards to affect the training process, not the magnitude of its value. Okay, now that we have seen this, I believe you should have most of the knowledge, I guess, to understand all of the paper, because the other part that they do is, okay, instead of just taking the language model and just training with the reinforcement learning, let's try to introduce some, first of all, let's try to introduce some very high quality fine-tuning data, and then we do another step of reinforcement learning, and then we do another step of fine-tuning, and then do another step of reinforcement learning. And this actually leads to a better model. Another actually interesting part of the paper is the distillation. So the distillation, I don't know if most people are familiar with what is distillation and how it works. So if you want, I can talk about it a little bit. Otherwise, I think let's go to sleep, guys. Let's see. So yes means let's talk about it. Okay, no problem. Please give big picture overview. I mean, bro, you can just read the paper yourself. Okay. Yes. Okay. More on distillation. Okay. So distillation basically means this. Imagine you have a. Imagine you are trying to. Imagine you are trying to teach yourself. Okay. Imagine you are trying to teach yourself graduate maths. That's one thing, right? Imagine you don't have any background on math, and imagine you learn it from a university teacher. It's two different things, right? Because if you try to learn it by yourself, you need to come up with all the strategies to learn math. But if you learn it from a professor, then the professor can also give you hints on how to learn it faster. So in the case of models, we have usually a big model. So let's call it Big Brother. and then we have a smaller model. What we want is, and then we have a data set. Let's call it a data set. So data set. What we do is we prompt the big brother, so the big model. Let's call it big model. Actually, I don't want to confuse people. So this is the big model, and this is the small model. So now, when we train language models, so how do we train language models? First of all, when we train language models, we do that in a self-supervised way. What does it mean? It means that there is no kind. It means that the language model is trained without annotating the data. It means that we sample a lot of text and we force the language model to learn to predict the next token given the context that comes before it. It means that, imagine we want to train the language model on the following text. For example, the following sentence, for distilled model, we report representative results, blah, blah, blah. Imagine we want to train the language model only on this green text here. What we will do is we will give it the word for, and we ask it to learn to predict the word distilled when it sees for. Then we give it the word for distilled, and we force it to learn to predict the word models when it sees for distilled. The beauty of the transformer is that all this process can be done in parallel, so we don't have to do it one word at a time. If you do the job of training a small model on reasoning just by itself, it will have much more difficulties. However, if you have a big model that has already been trained on a specific task, then you can use the big model to help the small model learn faster. How? When we train a language model on raw data, so in this case, for example, we said to the language model, when you see for, you should choose distilled. When you see for distilled, you should models. This basically is called the next token prediction task. And the way we do it is we force the distribution that the language model outputs, and this distribution is the goal of the language model. So as we saw before, the language model generates a distribution over all the possible next words. So it will assign a probability to the first word, next word, and to the second next word, and to the third next word, and to the fourth next word. And we ask it, okay, when you see for distilled, you should exactly this particular word, which is the word models. So you should choose the word models, and all the other words should not be chosen. So 0, 0, 0, 0, 0, this one should be chosen with 100% score. This is how we force the language model. By doing it on many texts, the language model learns to generate a distribution that very likely will generate this word models when it sees for distilled, and less likely to generate the others. If we do the same job with the small model, we will see that the small model will have a lot of difficulties learning at the same pace as the big model. Why? Because the big model has more parameters, so it has more flexibility in learning complex tasks, while the small model does not have this flexibility, so it will be much slow learner. So how can we distill the knowledge of the big model into the small model? We do it as follows. We take a database set of prompts, so a list of prompts. We feed it to the big model, and then we ask the big model to generate an answer. Not only the answer, we also ask it to generate the log probabilities at each step of the generation process. So before we use the sentence, where is Shanghai? Shanghai is in China, right? So imagine we ask the big model, where is Shanghai? The model will generate Shanghai is in China. But with because we have the word Shanghai, we also have the log probability of not only the word Shanghai, but also all the other words that we could have chosen in that position. We force the small model to learn not only to generate Shanghai, but we force it to learn the same distribution that the big model generated for the same position. So let me do it again. So imagine now we do a concrete example. Imagine we have a sentence where is Shanghai. Shanghai. We give it to the big model. The big model will generate an answer. What does it mean to generate an answer? It means that it will generate, first of all, a distribution over what is the next likely next token, which will be a list of probabilities where the word Shanghai will have a very high score, so maybe 0.6, and maybe the word pizza will be 0.1, and the word cat will be 0.05, etc., 0.05, etc., etc. Then we choose the word Shanghai, and we ask the language model again, where is Shanghai? Question mark Shanghai. Then it will choose the word is, but it will not just choose the word is, it will actually give us a distribution, and we choose the word is. It will give us a distribution that looks like this. For example, it will say, okay, the word is very likely, so it's maybe 70% probability. The word, I don't know, road is unlikely because it doesn't make sense, and the word, I don't know, hello also doesn't make sense, so it is even less likely. So for each position, we can generate the log probabilities from the big model, and we force the small model not to learn to just generate Shanghai, but to learn this entire distribution. Why? Because this gives a much stronger signal to the small model on what it should do, what it can do, and what it must never do, instead of just telling you should do this. It's a bigger signal for the small model to learn faster. And what they say in the DeepSeek-R1 paper is that by distilling, you can create a much stronger model than just by training them from scratch. A bit more context on the probabilities for each forward pass. Well, no, distillation is used on all the tokens. So it's you are telling for each possible token, you learn the entire distribution for each position, not only the last. So how we assign reward for each action? Okay, in the case of PPO. By the way, if you watch my video on PPO, I explain all of that. So I don't want to kind of I don't know why nobody ever watched that video. It's one of my masterpieces, and nobody ever cared about it. But all these slides come from my video that I done in 2023. So the way we generate the rewards is basically the rewards are usually only generated for the, okay, there are two kinds of rewards that you can generate. One is called the outcome-based reward, and one is called the process-based reward. In the case of PPO, we generate the outcome-based reward, and then through the advantage term it is kind of distributed on all the previous tokens, because we sample a response and then we judge this response according to our reward model. Then with the advantage terms that you see in the loss, this reward is distributed on all the previous tokens. So each token carries information on how likely it is going to lead to the final reward. Okay, there is another part of, I think we forgot one part, guys. The unsuccessful attempts. This is interesting also. So they tried what is known as the process reward model. Basically, okay, the reward model that we saw before is a rule-based model that is outcome-driven, means that the model have to generate the entire process, and for example, in the case of lead code problems, the model has to generate the final code to make it runnable. Then we run the code, we see how it performs, and then we have signal on the reward. However, there are other ways of generating reward, and one of them is called the process reward model, where you divide the problem in sub-problems, and then you have a model which is called the process reward model that assigns a reward to each single step. However, in the paper they say that assigning, first of all, dividing a problem into sub-steps, it's difficult because every problem is different, and we don't want to kind of tell the model you should follow this pattern. It should, the model that should try to come up with this pattern, and actually does. And secondly, they say that it's difficult to judge each single step. So sometimes we don't even know if that step is good or not. Like when you're trying to solve a math proof, sometimes you do some intermediate steps that may not lead to the you may not immediately see that they will lead to the final conclusion, but they are necessary, right? So it's difficult to give them a reward until you arrive to the end. So it's difficult to kind of give a reward to each single step. And there is another technique called the Monte Carlo tree search, which basically it's a tree search in which each intermediate node is given, each intermediate node is also a step, and each of these steps, each of these nodes actually has a kind of a score associated with it, which increases the more time that particular step leads to a successful solution. So imagine, for example, you are doing a leet code, and if you leet code problem. So if you start your code, for example, with a typo, of course the code will not compile. So anything that starts with that typo will never lead to a successful solution. So that node will never be explored further. So Monte Carlo tree search basically forces the language model to explore more of the solutions that lead to successful attempts and less to the one that don't succeed. However, even by doing Monte Carlo tree search, they get like sub results that are not as good as the reinforcement learning driven one. And the beauty of this actually is also in this sentence, which is rather than explicitly teaching the model on how to, first of all, divide the problem into sub-problems and how to solve the problem, or tell the model what is the format it should follow to solve the problem, the model just learns to come up with the right format, with the right chain of thought to solve the problem. Of course, they play with the reward, because they tell the reward that the language model should follow a particular format, and the language model should also, should be accurate, etc., etc. So you can always play with a little bit the reward. And another thing that they notice is actually, if you train the language model only on the reinforcement learning, then it leads to kind of the language model with some side effects. For example, the fact that the language model mixes languages, because nobody told the language model that it has to only speak English to solve a problem that is stated in English. So imagine I ask you to solve a problem like a math problem, and I say it in English. And imagine you are like a mixed kid and you can speak Chinese and English, or you are just a Chinese who knows also English, etc. Maybe in your head you speak English and Chinese, you think in English and in Chinese, and then you come up with this solution, and that's totally correct, right? So unless I tell you explicitly that you should never think in Chinese, then why you should not take the freedom of doing it, right? So if you never tell the model to not do something, the model probably will do it. And because in the reward here they never told the language model to never think in other languages, the language actually started thinking in other languages. Anything to get the job done. That's the beauty of reinforcement learning. So you give the right incentive and the language model will come up with the right way of reaching that goal, as long as the signal is strong enough. Yes, you need a massive cluster of GPUs, I believe so, because you still have you're still running gradient descent on the language model itself. So every time you are kind of fine-tuning the language model, you are changing its weights. So okay, guys, before we talk about other questions, all this lecture was totally kind of improvised, so I didn't prepare it. So I hope I didn't make big mistakes, because the problem is reinforcement learning from human feedback is quite a complicated topic, and you need to kind of derive everything step by step. This is what I do in my video on reinforcement learning from human feedback. Here I kind of sometimes skipped some steps, then went back, etc. So I hope I didn't create confusion. So if there is kind of some parts about the RL that you didn't understand, then I think we can talk about it. Otherwise, let's call it a day, guys. maybe you could record for YouTube more prepared. I could, but I have a daughter, guys. Now I'm super busy, and I also have a full-time job, and I also have a wife. So have some mercy on me. Thank you, guys. Yeah, I think everyone now should have at least the basic understanding on how to read the paper. Like when you read the paper, you should have a clear idea of what's happening. And if you kind of need more background, you can check like my previous works. I think let's stop the recording and have a good night, guys. And now if you want, you can also how to stop the recording.